Now we're going to define another group which has matrices at its core, but so it's again going to be 2 by 2 matrices with real entries, but not all of them. And the group operation is going to be matrix multiplication. So this set has a name, GL2 of R, and it's the collection of matrices A, B, C, and D, such that the determinant of the matrix is not 0. And the entries are all real numbers. And the reason for this determinant condition will be clear in a minute. And the group operation is matrix multiplication. So A, B, C, D, X, Y, Z, X, Y. Let's make this all a little nicer. Here we go. A, B, C, D, X, Y, Z, W is AX plus BZ, AY plus BW, CX plus DZ, CY plus DW. So if this matrix here is A and this matrix here is B, this matrix here is the product AB. So we have to check the group properties. So the first one is that matrix multiplication is associative. And I'm not going to do the calculation because it's a mess. But hopefully in linear algebra, you have seen the fact that this is actually true. And if you think about matrices as coming from linear maps, if you've seen that, then you can obtain this as a special case of the fact that composition of maps is associative. But you can also get it just by writing out the products and checking to see that because these terms just involve regular addition and multiplication, the associative properties and commutative properties of regular association and multiplication will let you show that for 3 matrices, this rule holds. Next, we need to know about the identity for this operation. And here the identity is what's often called the identity matrix. It's the matrix 1, 0, 0, 1. Because if you multiply a 2 by 2 matrix times the identity matrix, you get A, B, C, D. And similarly, if you multiply on the other side, you also get A, B, C, D. So the identity matrix is the identity for multiplication of matrices. The third property we need to check is the existence of inverses. That means if we have a matrix A, B, C, D, we need to find X, Y, Z, W so that the product is the identity. And in fact, here's where the condition about the determinant comes in. You probably know from linear algebra that if a matrix has non-zero determinant, then the matrix has an inverse. That is to say, if A is A, B, C, D, and AD minus BC is not equal to 0, then you can find A inverse so that AA inverse is the identity matrix. And actually, this is true for n by n matrices. For 2 by 2 matrices, we can say exactly what this inverse matrix is. If A is A, B, C, D, then A inverse is D over delta, A over delta, minus B over delta, minus C over delta, where delta is AD minus BC is not 0. So here we use the property that the determinant of this matrix is not 0, and then we can just check that if you multiply A times A inverse, that's A, B, C, D, D over delta minus B over delta minus C over delta A over delta, which is AD minus BC over delta, minus AB plus AB over delta, which is 0, CD minus CD over delta, which is 0, and finally minus BC plus AD over delta, and that's equal to 1, 0, 0, 1. So if the determinant AD minus BC is not 0, then we can find an inverse for this matrix. If the determinant is not 0, then you can't find a determinant of that matrix. You can't find an inverse for that matrix. And that I'm also not going to prove. I'll probably leave that as an exercise. It was something that you studied in linear algebra. So if delta is 0, then there is no inverse. But we don't actually care about that because we've limited our group to be the matrices which have non-zero determinant, and therefore every one of the matrices that has non-zero determinant has an inverse. One final comment, this group is not abelian. If you multiply 1, 1, 0, 1 times 1, 1, 0, 1, you get 2, 1, 1, 1. Whereas if you multiply 1, 1, 0, 1 times 1, 1, 0, 1, in the other order, you get 1, 1, 1, 2. And so you see these two things are not equal. And so this collection of matrices with non-zero determinant is a group, but a non-commutative group, non-abelian group. And maybe I'll just finish up by saying this notation, GL2 of R, GL stands for the general linear group. And the 2 tells you that it's 2 by 2, and the R tells you that the entries are any real number.